All right, let's dive into one of the most fundamental ideas in all of computer science, the tree data structure. Now, you might not see it, but it is the hidden architecture that powers so much of our digital world.
I mean, think about it for a second. Your computer probably has hundreds of thousands, maybe even millions of files on it. But when you search for one, you get a result in like a split second. How is that even possible? Well, it's not magic, but it is a really brilliant piece of organization.
So, the secret is that your files aren't just stored in one gigantic messy list. Nope, they're organized in a hierarchy, a structure that we in computer science call a tree. You know the folders, subfolders, and files on your computer? That's a perfect, real-world example of a tree in action.
Okay, so how does this structure actually work? Let's break down its anatomy, and we'll use that same file system analogy to make it super clear.
Every tree has to start somewhere, right? And that starting point is called the root. It's the one single node at the very top that doesn't have a parent above it. In our analogy, this is basically the main drive on your computer, the C drive, the top-level directory where everything else branches out from.
Now, this parent-child relationship is really the heart of the whole thing. Each item or node is connected. A node with items underneath it is a parent, and those items are its children. So think of your Documents folder. It's a child of the main drive, but it's also the parent to, say, the Work and Photos folders you have inside it.
And what about the end of the line? Well, a node that has no children of its own is called a leaf. These are your actual files, the documents, the images, the applications. They're the final destination at the very end of a specific path through that whole folder hierarchy.
So we have this really neat hierarchical structure, but it's not just about keeping things tidy. This organization is what gives computers a superpower: lightning-fast search.
This is where you really see the huge difference between a simple list and a tree. In a list, if you want to find one file, you might have to check every single item one by one. In computer science, we call that ON time, which basically means the search time grows directly with the number of items. But a tree lets you discard these huge chunks of data with every step. You open one folder and you instantly get to ignore thousands of others. It is exponentially faster.
This search superpower is perfected in a special kind of tree called a binary search tree, or BST. So, to see how it works, let's switch from files to numbers for just a moment. A BST has this one simple, really elegant rule. For any given number, everything in its left branch is smaller, and everything in its right branch is larger. That rule is the key to everything.
Let's see it in action. Say we want to find the number 57. We start at the root, which is 50. Is 57 greater than 50? Yep, so we instantly ignore the entire left side of the tree and just go right. The next node is 75. Okay, is 57 less than 75? Yes, it is. So we go left. Next node is 60. We go left again, and boom, we found 57. In just a few simple steps, we've navigated directly to our target.
And just think about what that efficiency really means. For a well-organized tree, you could find one item out of a billion in about 30 steps. 30! A simple linear search? On average, that would take 500 million steps. The difference isn't just big, it is absolutely astronomical.
But that incredible speed, it comes with a major catch. This superpower has a critical weakness, a real Achilles heel that can bring the whole system grinding to a halt if we're not careful.
This quote gets right to the heart of the problem. If you just keep adding atoms in an unlucky order, say numbers that are already sorted, you don't get a nice, bushy tree. Instead, every new item just gets tacked onto the same side, creating this long, crooked line. Your beautiful tree just becomes, well, a glorified list. And this table here shows you the two possible states. On one hand, you've got the healthy, balanced tree. It's bushy, it's wide, and it gives us that incredibly fast search speed we want. But if it becomes unbalanced, it gets all skewed and linear. And just like that, all that speed, it vanishes. You're right back to checking things one by one, making it no better than that slow, simple list we started with.
So how do we prevent this disaster? Well, computer scientists came up with some incredibly clever solutions. Self-balancing trees. Structures like AVL trees and red-black trees, they have these rules built right in. As you add items, they can actually detect when the tree is getting lopsided and automatically perform what are called rotations. They literally shift branches around to restore the balance. This makes sure the tree always stays bushy and wicked fast.
So now that we know how these trees stay balanced and fast, you're going to start to see them absolutely everywhere in computing.
And this concept's reach is just staggering. I mean, beyond file systems, trees are used to map out every possible move in game AI, from tic-tac-toe all the way to chess. They manage tasks in your computer's operating system, they help compilers understand math, and they even organize the layout of the apps on your screen. They are the invisible backbone of almost everything.
So at the end of the day, the tree is this fundamental way of organizing information into a hierarchy to get incredible speed. And now that you have this mental model, I'll leave you with a question. What other structures in your daily life, digital or otherwise, are secretly just trees in disguise?